Law of universal gravitation, or universal gravitational law. Let's write in green. Universal gravitation. Okay, so Isaac Newton, very highly intelligent human being. So like a few accomplishments were laws of motion, okay, which we sort of take for granted. They're just ubiquitous. We learn all about them starting at a young age, and you have to remember there was a time before people really understood how motion worked. Actually, Aristotle had his own views, of course, but ideas like inertia and force and so on, and how all these things are related, comes from Isaac. Invented calculus, although it was co-invented, not co-invented, but independently invented by Leibniz as well. But Newton had his own version of calculus that he used to figure out the law of universal gravitation. Now, Newton didn't work in a vacuum. Obviously, he inherited some scientific knowledge from people that came before. People like Johann Kepler, who did a lot of work with things like figuring out that the planets had elliptical orbits and so on. But Newton's leaps were fairly large in terms of the way that we think about the world. He also inherited some of this stuff for motion from Galileo. Math, there was inroads into calculus from ancient times, but he sort of brought it into the modern era, I guess. And then what we're going to study today is the law of gravity, and specifically the universal law of gravity. So the Black Plague hit London while Newton was at Cambridge, and he had to go home to the farm. And while he was there in his 20s, sometime in his 20s, he did kind of all of this stuff. Now, I'm not a Newton historian. I just have heard this stuff secondhand, or maybe in third hand. But anyway you look at it, if you can do all of this stuff before you turn 30 years old, good on you. So there's a famous story about Newton that says, and I'm going to draw the picture, because I don't know if this is a true story or if it's apocryphal. Is that the way to say that? In other words, it's like an exaggerated story that's become, considered to be true, or what? But it's the apple thing, right? Where Newton was hanging out in the apple orchard. Let's see if I can draw Newton here. Young guy, chilling out in the apple orchard, right? Just leaning up against an apple tree. Well, I think in one version he gets hit on the head. I'm going to draw what I think is the more reasonable version, if it ever happened at all. And that's that he's hanging out, and he suddenly sees a apple accelerate towards the ground, right? And at the same time, it's the time of year where you have a moon in the sky, even during the day. Okay, so he's able to see the moon. And when that happens, Newton's great, enormous mind comes to a conclusion. The same force that accelerates an apple towards the ground could also be responsible for keeping the moon up in the sky, right? Not generally something that you would say is intuitive, right? Apple is equal to the moon, or some version thereof. Okay, there it is. So yeah, whether or not this actually literally happened, who knows? I don't know where the story came from, but it's a nice way to think about and remember that Newton was able to make a connection between two fairly, I think the word's disparate, if you want, ways of looking, kind of like looking at the world. Okay, so disparate ways of looking at the world. They don't initially seem to be connected in any way, do they? Right? And you have to pardon the people that came before Newton for not really being able to make this connection on their own. Okay, so how could this be so, right? How does this make sense? So here's kind of an explanation of how you can think about this. It's possible that you've seen this little demonstration before. I do it quite often, but I think it's really quite a useful way of connecting these two things. So let's imagine that this represents the Earth. And yes, Newton did know that the Earth was round. That's been known since ancient times. Like when I say ancient, I mean like Greek times. The Greeks actually had a good measurement for the size of the Earth. We can someday go into how they were able to do that. Okay, so let's imagine you have a cannon sitting on top of a mountain, right? And let's say that you put the cannon on its lowest possible setting. Essentially, a cannonball just falls out the end and falls straight down to the bottom, right? But if you start to shoot cannonballs at higher velocity, so this is projectile motion, and you gradually increase that velocity, and you increase it, eventually you're going to get to a point where your launched cannonball actually falls in such a pattern that it literally misses the Earth, okay? So once this happens, if I jump my cannonball out of the way, well, this cannonball will like continue to fall and continue to miss the Earth forever, okay? And what we could say then is that this cannonball has gone into orbit, right? It's orbiting around the Earth, all right? Does that make sense? So something falling like an apple and something orbiting the Earth like a moon can both be under the influence of the same physical property, physical force, okay? So now, we started to talk about centripetal force, right? If something's in orbit, it needs a constant force on it, pulling it towards the center, accelerating it towards the center. So in this case, well, we call that the force of gravity. Okay, so it's the force of gravity on an object that is moving with some large velocity, okay, and pulling it towards the center of the Earth, that sets up this system of this orbital system of the moon going around the Earth. You can extend this logic to the Earth going around the sun, and the sun going around the center of the galaxy, and so on. Okay. Now Newton was also able to, with ratios, prove this to be true. That gravitational force, oops, on the wrong setting here. That the gravitational force is proportional to a few things. One, the masses of the two objects. So in this case, say mass of Earth and the mass of the moon, right? So M and M. And that it is an inverse law, and it's an inverse square law. So Newton was able to derive this relationship using calculus, okay? And within this, you get elliptical orbits. They're not perfectly round. You get elliptical orbits. And yeah, he was able to kind of prove this. Now, I don't have the math skills to repeat what Newton did or to drive it the way that he did. But once you guys learn calculus, because I know you'll go on to great things, okay, you can come back and show me how you pull this out of the information that Newton had at his disposal, which was elliptical orbits and some other planetary positions and so on, because I don't know exactly how. But I do know that we received this from Newton, okay? On its own is kind of a mighty leap in science, but a little later, a guy called Cavendish was able to actually find the mass of the Earth using an experiment. Well, actually, what he was trying to do was he was trying to weigh the Earth, basically. He was using Newton's relationship to find the mass of Earth. But what he did on the weigh was he actually found what's called the gravitational constant. So the form that you're going to see this in is going to actually be an equivalency, not just a proportionality, but an actual equivalency. So you come up with a value g, a constant, that you throw in here, and then you can actually pull out of here force in newtons. Okay. All right. And then the two masses of the objects you're interested in kilograms and a distance in meters. So here's a question for you. Looking at these input values, what units do you expect to find for g? Not Don't care what the number is, but what units must it be? How can we break that down? Well, this is newtons on the left. We know that it's got to be kilograms, meters per second squared, right? If we start to go through this side, let's see what we get. So we'll leave G out. So we'll just put it as a question mark. The units that we have are kilograms squared, and we have meters squared on the bottom per meters negative squared. So what do we have to multiply this by to end up in the units of newtons? So we would expect, and we'll double check just to make sure, but we would expect, that we'd have kilograms to the -1. We'd have cubed meters, right? And you'd have seconds to the -2. So this is kind of an insight into the way that things like constants work, right? It's essentially a corrective value, taking what you're inputting and converting it to the units that you want, right? As well as applying the correct scaling factor to it. So in other words, if this was measured in, say, pounds, and we want to come out in pounds over here, it would be different units, and we'd have a different number for it, okay? So in Newton's day, G was not known, all right? But later, Henry Cavendish figured out what G was, actually in 1797. So like roughly, I'm going to say just probably a little over 100 years after the days of Newton, they came up with this value for G. We're able to make a ratio into a universal law, okay? So how did he do that? How did he come up with what G was? Well, he ran an experiment. He did it experimentally. So I'm going to explain the experiment really quickly to you because there's some questions in your book sort of relating to it. So this is what he did. He hung gigantic masses. I'm going to say gigantic, but heavy masses. Probably lead weights, I'm thinking. Okay, let me just draw this picture. It's going to take a second here. You can draw it as well. Okay. And whoops, always. And there's a mass, and there's a mass. This is a thin wire. Okay, and this is called a torsional balance. And then we had two very large fixed masses. Okay, this is all going to make sense in a second. Okay, so what this is supposed to represent is a torsional balance. So this is fixed to the ceiling, say, and this hangs down. And first what you do is you take these very large, enormous masses out of the way, and you'd let this thing torque, and you'd find that it would oscillate back and forth, right? It would oscillate at some very predictable period, right? It's essentially like a torsional pendulum, it's a twisting pendulum. And Cavendish would look at that period, and then what he'd do is he'd move these large masses nearby, not quite touching, but nearby. And if you do that, well, there's a little wee gravitational force between these things, and it would actually like change the period. And I think what he actually, now that I'm thinking of it, did was he also attached a mirror to this. He attached a mirror, and he shone a beam of light off the mirror, which then like shone on the wall. He had markings on the wall, right? So this, I guess, amplifies the twisting and slows it down, or makes it easier to like calculate like how much twist you have. Now, I don't even claim to come anywhere near understanding how you go from knowing the twist without the gravitational force to mathing out the actual like value that he got. But by doing this, by figuring out what G was, okay, through the small, very small gravitational attraction between these masses, he was able to come up with a value for G. I'm going to tell you what it is. And with that, once you have G, you can actually find out what the weight of the Earth is. I'll show you how you do that in just a second. So this is the Universal Gravitational Constant. When you're dealing in SI, which we always are, you get this. And let's see what our units are. They're actually kilograms to the -2, and I just have it in terms of newtons, which makes it easier, to meters squared. Okay, which makes sense, right? You got negative meters squared on the bottom, right? You've got kilograms here, so you need kilograms, -2, and that gives you an answer in newtons. We actually were a little more precise, but there's a kilograms here, right? So kilogram meter per second squared works out to be this unit. So you end up in newtons at the end, which is kilograms meters per second squared. So there you go. So now let's do a question with this. Find Fg between a 100-ton mass placed 1 centimeter from another 100-ton mass. So gravitational attraction and gravitational force is based on mass. It's a property of mass. All mass attracts other mass, in the universe. So you and I attract each other. You attract the Earth attracts you. Your pen and your hand are attracted, and so on. It's just that it's a really, really, really small force. So in this case, Fg equals G, mass and mass, they both happen to be 100 tons, over d squared. So 6.67 times 10 to the -11, the units we want to come out in newtons. We want to cancel off mass, and we want to convert it to getting rid of distance, so meters squared. Okay, so that's that. And then our two masses are, well, 100 tons is 100 times 10 to the 3 kilograms, or 1 times 10 to the 5. And we're going to multiply that by itself, so I'm just going to square it, okay? Just going to square it because we're going to multiply it by itself anyway because they're both 100 tons. And then the distance is 1 centimeter. 1 times 10 to the -2 meters away. Do you think this is going to be a big or a small force? Yeah, so you actually get like a little bit of force on here. So about 67 newtons is what I'm getting. The next question is, though, like, how big is a 100-ton object? Can we think of a 100-ton object? Sorry, let's fix that. I forgot to square the d. Thought something seemed off. Let's think, because I had a square here, I screwed up. This has to be squared. My mistake. Classic mistake. So thinking of what weighs about 100 tons, we came across that a Boeing 757 weighs about that. And if we do the math correctly, by squaring the bottom, you actually get about this. Okay, so that you know what, maybe that seems high, but let's do this. Let's just see what kind of, if it would cause an acceleration, what would that acceleration be? About 0.07 meters per second squared. So not much. And that would have to be on a frictionless surface. Well, you are, right? So think about it. Let's try this. Huh. Oh, well, you know what? This is about, yeah, I don't know. I'm trying to think of what that would be like in terms of kilograms. It's like a tenth of that. Oh, that's pretty big. Let's figure out this thing about, what happens here. The other thing is, don't forget that it's got to do with both masses, right? It's got to do with a 100-ton object and another 100-ton object. You have much less mass than 100 tons, so you're going to be part of it as well. Except the paper does not weigh 100 tons. Maybe if you had like a 100-ton piece of paper, but then, you know what I'm saying? Here, let's try it. Let's try a more like familiar example. Why don't we try this? here's you, and here's like a really massive object, the Earth, right? So how far are you from the center of the Earth? Yeah. What's the radius of the Earth? Do you know what it is? It's about 6,000 kilometers, I think. It's about 6,370 kms. Right? Or 6.370 times 10 to the 6 meters. Okay. Let's also figure out, so that's the distance you are away, right? R. And let's figure this out. Okay, your mass, let's say you weigh 100 kilograms. Let's say the mass of the Earth is what it is, which is 5.97 times 10 to the 24 kgs. Can you figure out what the force on you should be? Now the distance is r, so r squared. Okay. All right. Two masses on here. You've got your mass, you've got Earth's mass. And your mass all over this value squared. Okay. What do you get for Fg? So this is going to give you, you do this math, you'll get roughly about 981, approximately 981 newtons. Now, the reason that that should not be surprising to you is because you are now doing this in a different way. Before we said that your weight is equal to your mass times g, the acceleration due to gravity, right? So you've got 100 kilograms times 9.81 meters per second squared. Well, lo and behold, 981 newtons. So there's agreement here between acceleration due to gravity and Earth. So check this out now. Hey, I weigh 100 kilograms. So Fg equals mg, and Fg equals big G m all over r squared. So let's check something out here. Okay, let's see what we can do with this. Can we define G in terms of Newton's law of universal gravitation? Well, the answer obviously is yeah, we must be able to, because using little g and using this big formula give us the same answer for the force of weight that would be on your object, right? We call this weight. We call this weight. So if we make these two equations equivalent to one another, we can pull something out of there. So we could say that mg should be equal to g big M little m all over r squared. Well, if you see on both sides, the mass of the smaller object becomes irrelevant. You can scratch it off. And this should maybe give us a little bit, maybe it's only mathematical, but some insight into whether or not it should matter how much the mass of the secondary object is in terms of finding its acceleration. The answer is it doesn't. And so mathematically, from Newton's equations, you can kind of figure out that the acceleration of an object, of a smaller object in the gravitational field of a larger one, is irrelevant. In other words, all objects accelerate at g, right? And g, you can also see, would be different depending on what planet you were on. So let's say you go to the moon, right? The radius gets smaller, but the mass gets smaller, okay? So what is the acceleration at the surface of a planet equal to or related to? It's related to a few things, right? Oh, I need to use my circle drawer. That looked horrible. So if I'm on a planet, right, figuring out the acceleration at the surface of the planet takes into account m and r. and that's it, right? So, a really large planet with a low mass, well, what's going to happen there, right? It's going to have a fairly low g. But if the planet is very massive and it has a very small radius, g is going to be very, very large, all right? So this gets into the interesting questions where you could say, like, I'm on the surface of a neutron star with this radius, the radius the same as Earth, but with density equal to a neutron star. Well, what mass is it going to have? And then what g value am I going to have? And this is where you get insane values of g, right? And if you have that, right, then you can go back and you can figure out, what sort of weight would I have on a planet like this? And you get these ideas of like a teaspoonful of matter weighs tons and tons near the surface of these gravitational objects, okay? So there's some interesting math that we can do. And we can also do something else now, all right? We can realize that for the most part, objects orbiting other objects tend to do so in roughly circular patterns, right? Technically, they're elliptical, but the elliptical nature of an orbiting object is quite small. It's not a super exaggerated ellipse, at least for most objects. I mean, there's definitely things like comets and stuff that have highly eccentric orbits, but most are like nearly circular, especially for planets. So we can do some other things with this math now, okay? So if we assume, I know you hate that word, but so we have a little bit more complex math, we're going to make that assumption. If we assume circular orbits, we bring in our centripetal force math. Okay, so there's the center of the planet, and here's some object, say a satellite or whatever, orbiting above the planet, right? Zipping around like that. So we could say this, right? We could say that the centripetal force, in this case, is provided by gravity. That makes sense, right? It's gravity providing a force aiming towards the center at all times that keeps us in its nearly circular orbit. So what we should be able to do then is make some stuff equal to some other stuff, right? We could say mv squared over r, which is also equal to, we figured out before, m4 pi squared r all over t squared, can be equal to our force of gravity stuff, mg, if we know what g is, or better, g mm all over r squared. Okay. Now have a look. What appears on the top of everything here? M does, right? M does. So what we're saying here is if we're talking about like a planet and a satellite, the satellite would be the little m. Or if we're talking about a star and things orbiting the star like the planets and so on, right? We could be talking about those planets as being the little m's. Now, again, we're exaggerating because you're probably sophisticated enough to realize stars are not set dead still, and the planets going around them actually do cause wobble, okay? But we're going to do some approximating here just because the math that we have is maybe a little bit, it's not quite there where we can account for wobble at this stage, okay? So we're making the assumption that the central object is stationary and the other objects are just zipping around it, okay? So what we're going to do is we're going to realize that we can pull mass right out of this equation. And we end up with this whole big relationship, okay? So this we found before. And what we could do, right, is we could then figure out like what g is, what acceleration we'd have due to gravity at different heights from the center of the Earth, right, or from the center of whatever planet. So you could talk about things like, what is the acceleration due to gravity, when we're up in an airplane, say, or when we're on the International Space Station and so on. And you'll realize pretty quickly that the acceleration due to gravity, does not decrease all that quickly as you go up, So if you're, say, like, I don't know, let's say you're like 1,000 kilometers above the surface of the Earth. Well, what's g going to be at 1,000 kilometers above the surface of the Earth? There'll still be a g, but what does it change to? So we could go G is equal to gm over r squared. Okay. All right. Keep our units in there. Newtons, kilogram, negative squared, seconds, not seconds. Oh, don't go away. There we go. Okay, then you need the mass of the Earth, which I think we had at 5.97 kilograms. And now we're at a radius above the surface. So we had, I think, 6,300 kilometers, or now 7,300, so 7.3 times 10 to the 6 meters. Square it. Let's figure out what G would be. I get about 7.5 for G. All right. So, and actually this should be 24. So then this always begs the question, okay? If I go up above the Earth 1,000 meters, and I'm in, say, a space station or something like that, if I were to stop this dead, I would still be experiencing, an FG equal to m times this value, right? Actually, just is what it is. Whoops. I would experience an FG equal to that, right? So I would still have a weight, and yet when I'm doing this, I feel weightless. Okay, why is there an apparent weightlessness to someone that is in this scenario? Why is that? If there's still gravity there, why do they feel like there isn't? Yes, exactly right. So going back to Newton's example there, imagine that we, instead of shooting a cannonball, we shoot a tin can, and we shoot a person at the same time, right? And then we just happen to throw the person in the tin can in such an orientation that the person's inside the tin can. They are both falling equally. Or you could think of it this way. The tin can is following this path, right? Getting pulled towards the Earth. If you put a scale under this person, right, the scale is always falling away from them, right? Now the scale is getting pulled with Fg. You're getting pulled with Fg, force gravity, and the whole tin can is getting pulled with Fg. So the relationship between these things does not erase your weight, but it erases your ability to weigh yourself, essentially, right? What you're going to feel as weight is the normal force of the floor pushing back up on you. You can't have a normal force if you're both essentially falling. It's the equivalent, really, of being inside an elevator that is falling, towards the Earth in a gravitational field. These are like equivalent scenarios.